Hello and welcome to Sets Sheet 4, my Formalising Mathematics 2022 course. So the first three sheets were about completely abstract sets called things like A, without any definition really. They were just like let A be a set. And what's going on here is I thought I'd actually show you how to make sets, like kind of concrete sets of numbers, like the even numbers or whatever. So here's a lemma mem def. So the notation is this. That's the set of elements of x, the set of elements of x that satisfies some property p. Looks like that. So it's that sort of that slash sign, that pipe sign, is part of the syntax for sets. And x is in that set if and only if p of a is true. That's true by definition. So let's have a look. What are we doing here? We're trying to prove that 74 is in the set of natural numbers which are even. So you see I could use change. I could say that's change is even 74. Because you see that's true by definition. And the definition of is even is there exists a t such that n is 2 times t. So we could even unfold is even. There you see. And the goal has now become there exists a t such that 74 is 2 times t. So nothing has happened so far, right? We've only changed the goal up to definition, and so the goal, we could copy that there. We could just do change that, and then we could get rid of those, and that's all sort of fine. And now how are we going to do it? The answer's 37, right? So use 37, and now we've got to prove that, and norm num will do that, right? There. So in fact, I guess we could do exact pointies 37 comma by norm num. That would probably do it as well. Yeah, there you go. So, or I mean, maybe I'll comment that out. That works. So use 37 norm num also works. So now what? So that's the theory of even natural numbers. Now let's develop the theory of even real numbers. A real number is even if it's twice another real number. So let's prove that every real number is even. So intro x, and now again I'm just going to unfold this in my head, right? I use dot notation. Isn't that clever? Real dot is even r has been abbreviated to r dot is even. R is even. It's great. Sounds like English, right? It's clever. R is a real number. X is in the real numbers are such that r is even, and the definition of r is even is there exists. So the goal is there exists a t such that r is 2 times t, and that's true because I guess x over 2 is going to work. So use x over 2, and now that. I guess norm num won't solve it because it's got a variable in. Let's just check. There you go. It doesn't solve it because there's things that aren't numbers. Norm num is for normalising numerals, but the ring tactic should do this. It does. We're rather lucky that the ring tactic I think didn't used to do this, and we're rather lucky it does it because division is not a thing in rings if you think about it. You can't like a general ring. There's no division. So how come this has worked? It's because somehow the ring, I think the tactic has sort of special, it'll let you divide by positive naturals basically. Now I've sort of got intrigued actually. Okay, minor distraction. Example, let's have x is a real number. Will it work for negative reals? X over negative 2 times negative 2 equals x. Can't equals by ring. Oh, so it works for negative integers as well. And would it work for I don't know? Would it work for rationals? Let's try x over 2/3 times 2/3 equals. There you go. Isn't Mario so smart? Ring is such a powerful tactic, right? That's not an assertion in the language of rings, right? And in some rings it's probably not true, or like if you've got rings of characteristic 2 or 3. But somehow it must know that the reals has got characteristic 0. Okay, mental note, ask Mario how this is all actually working. Let's finish the sheet. What have we got to do here? Oh, yes, we're developing the theory of positive, negative real numbers. So we could do. So does Linarith just do everything? No. So let's get Linarith to do it. So intro X. Try Linarith now. Does it see through it? No. So I'll tell you what we could do. Here's a way of using the rintro tactic. Rintro X HX. HX, this is definitional. You could say what the type of HX is. So HX means HX is the same as 0 is less than X and X is less than 0. And you can tell it to call it that, I think. 0 is less than X and X is less than 0. There, you see, now H, because I'm only changing things up to definitional equality. And now I think Linarith might do it. There you go. So there's a rather nice short proof of that. Oh, and it looks like that's the end of this video. Thanks for watching.